and Xuan, I will be sharing our work titled LVT, Large-Scale Scene Reconstruction via Local View Transformers. LVT is a feed-forward Gaussian Splat method for entire scenes. Compared to vanilla 3D GS in the upper left, which is optimized per scene, our model is both higher quality and orders of magnitude faster using a single inference pass. I'll start with some high-level motivation for our problem. For scene-level reconstruction, we often have a large number of input images, more than just the 9 shown in this example. And in this work, we assume known camera parameters throughout. We build off recent developments in vision transformers as our model backbone. And this produces a scene representation that we can then render to a target camera. However, a core module in the transformer architecture is a self-attention block. And this scales quadratically with the number of input images, making it harder to scale to increasingly long and high resolution scenes. So, motivated by the insight that spatially nearby views provide a more useful signal about local scene structure than distant views, LVT processes information in a local neighborhood around each view, rather than using a fully dense attention operation. We consider each view as a central input for its own window, and we compute the spatially closest cameras to use as neighbors. We use a different set of neighbors for every input view. Intuitively, similar to how stacking CNN layers increases the receptive field, as we stack multiple LVT blocks, we expand the information flow beyond just the immediate nearest neighbors. For more details on our architecture design, first we take our input images and their camera parameters, and we use a convolutional layer to patchify the images with local redirections. This produces the image tokens associated with each image. We then feed the input tokens into our proposed LVT block. Our local view transformer block first extracts the neighboring token for each view by proceeding in the windowed fashion that we described earlier. Then, to provide awareness of the spatial arrangement of the image tokens, we take the camera extrinsics associated with each image, and we embed these as conditioning into each attention block, using their pairwise relative rather than absolute world transformations. After this local attention operation on each window, we follow with a standard residual feed-forward block. And we repeat the sequence 24 times. The tokens, which are now processed by the LVT blocks, are unpatchified and decoded to per pixel Gaussian Splat parameters. Specifically, our Gaussian parameters include the position, rotation, scale, and color spherical harmonics, which are standard quantities, but we also predict density using spherical harmonic coefficients to further help capture a learned importance over local views. The decoded splats are then rendered to target views using the 3DGS rasterizer and compared against the ground truth for loss computation. Compared to previous approaches, we use a novel camera conditioning tailored to our windowed attention. Prior works typically compute book arrays in a world coordinate system and embed these arrays into an array map. But since this is reliant on the choice of world coordinate used to define the entire trajectory, generalization is more difficult on out-of-distribution camera paths. Instead, given a center view and a neighboring view, we compute the relative transformation between every pair. And this relative transformation is encoded into conditioning features that are injected into each LVT block. Moving the spatial conditioning to the attention block is important for us, as the relative transformation of the center view to its neighbors differs for every window. And now, this is agnostic to the choice of world coordinate, and combined with our local window design, it helps improve generalization on view. view scenes. To briefly recap, the key adjustments that we make to LVT compared to prior vision transformers for novel beam synthesis are that we patchify using local ray directions rather than multiple coordinates. And instead, we use the camera extrinsics to compute the relative transform conditioning for window detention. This design is more robust to the number of images and camera trajectory, as local segments of camera movement are likely to be more similar across different scenes than the entire trajectory as a whole. Next, our decoder adds an additional view-dependent density prediction for improved rendering quality. Now I will briefly present some of our results. I'll start with a runtime comparison of our local attention and full attention operations on equivalent models. Our LVT blocks scale linearly with the number of inputs, where our standard full attention scales quadratically. We compare our model to 3DGS, which is optimized for each scene independently, the long LRM baseline, which uses a combination of full attention and normal blocks with a fixed number of inputs, our base model without view dependence, and our full model with added spherical harmonics. We also show the depth rendered from our full model. We find that our full model captures thin structures in the scene better than the other baselines. So in the red box, you can see that the banner is better reconstructed and sharper in our full model than in prior work. And from a single forward pass, here is a fly-through rendering of our model. And this is the predicted depth. These panels show the same rendering trajectory on 3DGS, long LRM, our base model, and our full model jointly, where you can see our full model yields the sharpest results, particularly if you look at the plant in the middle. This slide compares the result of 3DGS and our model when applied zero shot to a separate data set, the train scene from days and nights. Our method is much faster and higher quality. And this visualization shows the truck scene again from days and temples, where we can see more flicker and floaters in the 3DGS baseline. We can also do the same for Mittner 360, where we note that these scenes have an out-of-distribution camera trajectory compared to our training scenes. On this slide, we visualize the model without view-dependent opacity on the left and added view-dependent opacity on the right. Visually, this improves modeling of specular reflections and thin geometries, and quantitatively, adding this view dependence to splat opacity boosts performance on all metrics. Here's another visualization where we can see that specular reflections are improved in our full model on the right. Here, we hold the rendering camera fixed while changing the view direction. And you can see that the view dependence in opacity does help us capture reflective surfaces. We also experiment with a variation of our model for higher resolution. And for this, we patchify the inputs with a larger task size and use a feature fusion module to merge high resolution input features with a decoded output, yielding crisp, high resolution results. As demonstrated by our results, our local view transformer enables flexible and generalizable reconstruction and rendering of scene-level content from a single input pass. Thank you for listening, and for more details, you can visit us at our website.